Hello everyone, artificial intelligence and machine learning neural networks. In this video we are going to discuss vanishing gradient problem, hyperparameter tuning, batch normalization, regularization and dropout. Objectives of this video is to enable the students to learn vanishing gradient problem, to know the need for hyperparameter tuning, to understand batch normalization, to learn regularization and to drop out in neural networks. What is unit saturation? It's sometimes also known as the vanishing gradient problem. A sigmoid neuron will look like this, a smooth variation, but a perceptron will have a sharp change here, and a sigmoid neuron will have a smooth variation. Finally, it will flattens, it will saturate. Once the output saturates, what will happen? When you find gradient, first derivative, the first derivative will vanish. That's why it's called vanishing gradient problem. Saturated neurons thus cause the gradient to vanish. A sigmoid neuron is said to have saturated when sigma of x, the sigmoid output would be 1 or sigma of x equal to 0. So here it saturates, here also it saturates. So what would the gradient be at saturation? So it would be 0. So why saturation? Saturated neuron thus cause the gradient to vanish. Why would the saturation? So what would happen if we use a sigmoid neuron to initialize the weights to very high values? If we initialize the weights to very high, neurons will saturate very quickly. When we initialize with small weights means it will take time. When you initialize with large weights means what will happen? It will saturate very quickly. The gradients will vanish and training will stall, because once the gradient becomes 0, then back propagation will halt, because back propagation mainly depends on the first gradient. Tan H function compress all the inputs to the range -1 to +1. What's the derivative of this function would be this tan H function. The gradient still vanishes at saturation, also computationally expensive. This is a ReLU function. It's a non-linear function. We can combine two ReLUs against a sigmoid function, a piecewise linear approximation of the sigmoid function. When you combine two ReLUs, again it will be a non-linear function. When you find for the positive of alone, we will not be having any saturation problem here. Advantages of ReLU: it does not saturate in the positive region alone. Computationally efficient. It practice converges much farther than that sigmoid or tan H. Difference between model parameters and hyperparameters must be determined using model parameters. Must be determined using training data set. These are the fitted parameters. Hyperparameters, adjustable parameters, that must be tuned in order to obtain a model with the optimal performance. Model parameters. So in our case, W and bias, they are the model parameters which are going which through the model we will learn W and B. They are the model learnable parameters. Hyperparameters, in gradient descent you will have a parameter called eta. Eta is a learning rate. So learning rate, you will tune the learning rate to increase the performance of the model. That is not we are going to learn. We will tune. We will set some value there. Then we will increase or decrease, so that the performance of the model will be increased. That parameter is called hyperparameter. Hyperparameter tuning. We have to tune the hyperparameter to improve the performance of the algorithm. Consists of finding a set of optimal hyperparameter values for a learning algorithm while applying this optimized algorithm to any data set. For any data set, so you tune the hyperparameter so that the model is applicable for any data set. That's called hyperparameter tuning. The combination of hyperparameters maximizes the model performance, minimizes a predefined loss function to produce better results with fewer errors. This is a Bayesian optimization. This is a Bayesian optimization. Because of this tuning, this is called tuning. You tune it and the hyperparameters, through the hyperparameter we are optimizing Bayesian optimization. And regularization. Next is regularization. Why do we go for regularization? Regularization is we are adding some penalty there that will have what effect it will have. We try to reduce overfitting. What is overfitting? Overfitting, the model works well for the training data set, but it won't work. It will fail massively for testing data set. That is called as overfitting. This is first is for a L2 regularization. This term is the L2 the square term. For stochastic gradient or its variance, we are interested in the gradient plus alpha W. This update rule will become like this. Regularization is mainly used to minimize or to avoid what? Overfitting. Dropout is a technique which addresses both these issues, that is overfitting and all. Effectively, it allows the training several neural networks without any significant computational overload. Also gives an efficient approximate way of combining exponentially many different neural networks. We will initiate the parameters of the start training. first we'll drop out this. That means we'll remove the connection. Node will be there, but we'll remove all the connections. No incoming, no outgoing there. Okay, we compute the loss and the propagate. Which parameters will use? Only those are active, only those are connected. Okay, that only will update. So for the second training instance of mini batch, we again drop some resulting in different thin network. We again compute the loss and propagate to the active weights. If the weights are active for both the training instance means then it will get 2 updates. If it's active for only one means it will get only 1 update. Each thin network gets trained rarely or newer, but the parameter sharing ensures that no model has untrained or poorly trained parameters. This is the role of dropout. So if present with the probability, if that weights are present with the probabilities, it's always present. This is always present. So at training time, at test time is always present. With what happens at test time? Impossible to aggregate the outputs of 2 power thin networks. So how many thin networks you will be having? You will be having 2 power we are having n nodes. Instead we use a full network and scale the output of each node by a fraction of times it was on during this fraction of time. P is the fraction of time it is on during training. We can scale it. So the HI learns to detect a face by firing on detecting a nose, dropping HI that corresponding erasing all the information that the nose exists. So the model should learn another HI which redundantly encodes the presence of what? Nose. Or the model should learn to detect the face using other features. That way we will be able to reduce the overfitting. Batch normalization again is used for what? To reduce overfitting. Allows to be less careful about initialization. To understand the intuition behind batch normalization, let us consider deep network, focus on learning process of the weights. We can use mini batch algorithms. What would happen if there is a constant change in the distribution of S3? There is a constant distribution of S3. In other words, what would happen if across many batches, distribution of S3 keeps changing? The learning process will be very odd. So pre-activations and unique Gaussians, by standardizing the pre-activation, by this pre-activation, so just you change the mean and the values, you are normalizing it. That's why it's called as batch. That batch alone is normalized. Then we compute. How do we compute this? We can compute to a mini batch. We are expecting the distribution of the inputs at different layers does not change across the batches. This is what the deep will look like with batch normalization. With batch, this tan H after batch normalization, tan H, then batch normalization, tan H. Then tan H layer is differentiable. That batch normalization is also differentiable. Tan H is differentiable. Hence, we can propagate through this back layer. Layers. So, do we necessarily want to force a unit Gaussian input to the tan H layer? Why not the network learn what is best for it? After the batch normalization, this is after this batch normalization, and we have new variance and the mean, we have SIK. Otherwise, by adjusting these additional parameters, the network can learn to recover SIK if that is more favorable. This is MNIST database. The MNIST is a very standard database, handwritten letters database, MNIST. The left one is with batch normalization, the right one is without batch normalization. So with batch normalization is blue color, that shows lesser loss function. These are the references I have made.